So just a recap of last time, we proved some space lower bounds for streaming algorithms, for one pass streaming algorithms via communication complexity. And we did it via establishing that some communication problems were hard and then reducing those hard problems to our streaming problems. So for example, one way to get a lower bound for distinct elements, a linear lower bound, is via reduction from equality. You can even do it for you can reduce deterministic deterministic equality to deterministic approximate F0. Indexing was another one. I didn't show the reduction to gap hamming, but I claimed that it can be done. And then gap hamming can be reduced to randomized approximate F0. And that's how you get a 1 over epsilon squared lower bound for randomized approximate F0. You can also reduce it to randomized median. So the stuff in blue is some stuff that I want to show you today, and then we're going to be done with this and move into dimensionality reduction. So a new topic, we're closing the chapter on streaming, okay, after I finish showing these things in blue. So this thing is probably something you all are familiar with now because you had to show it on the p-set, right? So p-set 1, I forgot which problem. 3b, okay. So p-set 1, problem 3b, you had to show that randomized exact distinct elements requires omega n space. And then now you'll see it's basically, if you had known about indexing, which intentionally I didn't let you know about it because I wanted you to see more hands-on, some other approaches to proving it. But once you have indexing, it's almost like a one-line proof that randomized exact F0 requires linear space, okay? So now that you've struggled with it yourself, you'll appreciate the power of indexing. Okay. I'll also show you, so we showed that there's a 1 over epsilon squared lower bound for randomized approximate F0. I'll also show you that there's a log n lower bound. So in other words, the max of the two, or the sum of the two, is a lower bound. Right? They're both lower bounds. And I'll also show you that there's a problem called disjointness that can reduce to fp when p is bigger than 2, and show that for p bigger than 2, you need polynomial space. I'm not going to actually prove the lower bound for disjointness because that would take certainly at least one lecture to prove that, if not a little more. And I don't want to devote that much time to it, but I'll give you the reference, and you can look at that if you wish. It's similar to the way that we used information theory arguments to get the lower bound for indexing. Disjointness, some of the proofs for disjointness use a similar approach. They're just even more involved. Okay. So, and let me put it next here. Will be dimensionality reduction. So we're done with streaming after this. Okay, so let me first show this one, that the thing that you showed on the p-set 1, problem 3b. Okay, so claim randomized exact F0 requires omega n space. And when I say randomized, I mean the failure probability is a third. It's some constant less than a half. Okay. Proof. We're going to reduce from indexing. Okay. What does Alice have? Alice has some x, which is in 0, 1 to the n. Bob has some j, which is an index into x. Okay. And you're used to it by now. Alice is going to do the usual thing. If xi is 1, she puts I in the stream. Otherwise, she doesn't. Alice runs. So what we're going to do is suppose we had a randomized exact F0 algorithm. We're going to show that we can solve indexing using it. So Alice runs alg, the streaming algorithm, on x, and sends, what does she send? The space contents the memory contents. Maybe I'll say memory. And then she also sends the support size of x. To Bob. Bob then just appends J to alg, to the stream, sorry. Then queries F0 from alg. Okay? So what happens? Well, if j was already in the stream because xj was 1, then F0 doesn't change. He knows the support size because Alice sent him the support size. Right? So he just checks whether or not F0 increased from the support size. If it increased, that means xj was 0. If it didn't increase, that means xj was 1. QED, that's the whole proof. Okay? And well, just to wrap it up, you know, how many bits are communicated in this communication protocol? Well, it's a space S algorithm, right? Plus she sends the weight of x, the support size of x. The support size of x is a number that's at most n. So to communicate, it takes log n bits. So the total communication is s plus log n. Right? And you cannot solve this problem with communication less than the lower bound. The lower bound is some constant times n. Indexing requires omega n bits of communication, right? So just move the log n over. Log n is almost nothing compared to Cn. This implies that S is omega n. Okay? So there's your p-set 3b in basically one line. Yeah?
So why does randomness doesn't influence the communication?
Why doesn't randomness influence the communication? What do you mean by that? Yeah, so, you know, so let's, let me be a little more precise. So let's say random exact F0 with failure probability 1/3, let's say, requires omega n space, right? And we're going to reduce from index sub 1/3, which to me means the index problem where you have to solve it with failure probability 1/3. And we know that index 1/3 requires Cn bits of communication. So Alice runs alg. What is alg? Alg is a randomized exact F0 algorithm with failure probability 1/3. When does this communication protocol fail? It fails if and only if alg fails on that single query. But alg fails with probability 1/3. So we're solving index with failure probability 1/3. Does that answer your question? Okay, good. So anyway, yeah, that's it. So questions about this? Yeah, indexing is a very powerful primitive for lower bounds. And sometimes the way you use it ends up actually being somewhat tricky. I didn't show you this index to gap hamming thing, but it's a little more involved than some of the things I showed you. Not too much more. It's still simple, but I'm not going to spend time on it. OK, good. So now I showed you that arrow. Let me show you this one. Let me show you that randomized approximate F0 requires omega log n bits. Okay. So before I do that theorem, you can find a proof of this theorem, for example, in Cauchy-Levitt's-Nissan in that book I mentioned on communication complexity, which says that for any function f, for any communication problem, okay, so for any communication problem, f is your communication problem, let's say 2 players, the randomized private communication complexity. So this is the communication cost of the best randomized protocol for f with private coins with 1/3 failure probability is at least omega the determinist log the deterministic complexity. Okay, that's a theorem. I don't want to spend much time on this proof, but I'll give you a proof sketch. It's a very simple idea. Basically, what I want to show here is that if there's an S-bit, if there's an S-bit randomized protocol, then I'll show you that there's a 2 to the S-bit, roughly, deterministic protocol. Okay. Right. So how do I want to do this? So okay, so basically, let me write it like this. The essential idea is Alice has her private input X, Bob has his private input Y. Okay? Now Alice, let's say Alice is the one to speak first. So she has some private coins that Bob doesn't know about, right? Based on what her X is, she's either going to go to this node. There's kind of like a decision tree of how the communication between them is going to look. So she's going to flip a coin, and she's going to flip some coins, and based on that, she's either going to speak this or speak that. Okay. Let's assume that this is without loss of generality. Every time they each speak just like a bit. Okay. This blows up the total communication by almost a constant factor. So Alice is going to flip some coins, and based on the outcome of those coins, she's either going to go this way or this way in terms of what she's going to communicate. Now Bob sees what Alice communicated, so he knows which edge you went down. And then based on his input, he's going to flip some coins privately. And based on those private coins, he's either going to, so not S leaves, sorry, 2 to the S leaves. So the height of this, since the communication is S, the height of this tree is S. The height is the total amount of communication, like the maximum leaf depth is S. So Bob is going to know what Alice said, so he's going to know kind of where in the tree we are, and based on that, he's going to flip some coins and either communicate a 0 or 1, et cetera. Okay? Great. So how are they going to, if they have a randomized S-bit protocol, I claim they have a 2 to the S-bit deterministic protocol, roughly. And how does that go? Basically, for every leaf, Alice looks at the root to leaf path going to that leaf, right? Or for some other leaf, she looks at the root to leaf path going to that leaf. And she just asks herself, okay, pretend I'm here. What's the probability that I would go to this node? And now suppose Bob decided to go here. Given that, what's the probability that I go to this node, et cetera? So what she calculates is, assuming Bob keeps us on this path, what's the probability that I'll always keep us on this path? And that's some number. And Alice is just going to send all those probabilities to Bob for every single leaf. And then Bob is going to do a similar calculation. And based on that, he's going to know the probability distribution of the protocol. He's going to know what's the probability that if we actually had done the randomized protocol, for every leaf, what's the probability we would have ended up at that leaf? Okay. And then he can figure out kind of which leaves. Based on that, he can figure out basically whether the answer is yes or no. Okay. So there's some issue here. We have to like round the probabilities because you're communicating bits here, but you can show that you don't have to specify the probabilities up to too much precision. At the end of the day, the total communication is 2 to the s times poly s or something. So you kind of get the reduction. Okay, so I'm not going to, if you really want to see this, it's not a long proof, but if you really want to see the details more carefully than what I just said, look in the book. But let's just take this as a theorem. Okay. Good. So now that we have that, remember that we said, well, just like before, let C be a subset of 0, 1 to the n, such that for all C in C, the support size is exactly n over 100 or something. And for all C prime in C, the Hamming distance, like the number of agreements, back when we did the exact, or the deterministic approximate F0 lower bound, we showed the existence of a collection of subsets with this property. So here what I'm saying is kind of every subset I'm just identifying as a bit string, which is the indicator vector of that subset. Okay, so this is a subset of size exactly n over 100, meaning they're exactly n over 100 ones, corresponding to what's in that subset. And for every pair of distinct subsets in the collection, those subsets don't really overlap that much, right? And also we want that the size of C is at least 2 to the omega n. By the pigeonhole principle, deterministic equality on C requires omega n communication. Right. In particular, it requires log size of C communication by the pigeonhole principle. Okay? But then by that theorem, this implies that the randomized 1/3 private communication on on C, let's say, is at least omega log n. But now there's a reduction. There's a reduction, a natural reduction from XC, from randomized private XC to randomized approximate F0, right? So Alice and Bob each have a set in this collection, and they want to know, are these two sets equal? Or I'm viewing the sets also as binary strings, right? So we do the same thing as always. Alice takes her input vector. For every 1 in that vector, she puts it in the stream. She runs the algorithm and sends it over to Bob. Bob then inserts all of the elements from his set into the stream and then checks F0. If the two elements had been equal, then F0 would be n over 100. If the two elements were different, well, the answer would be kind of n over 50 minus their intersection. But their intersection is tiny compared to n over 50. Their intersection is n over 2000. So basically, based on whether or not those two sets were equal, the F0 answer the actual F0 changes by almost a factor of 2. So if you have like a 1.1 approximation, let's say, you can distinguish those two cases. So you've reduced XC to randomized approximate F0. Therefore, randomized approximate F0 must take log n bits of communicate. Must take log n bits of space. So what we've shown is that finally, the lower bound for randomized approximate F0 is 1 over epsilon squared plus log n, which turns out to be the truth. There is an algorithm that achieves that. Okay. And now let me show you the very last question. Oh, okay. Yeah, I mean, one thing many people do is just like handwrite it and then.
Yeah.
Oh, okay, okay. Yeah, instead of line checking. But any other questions?
So this claim, did you show that last time that deterministic is required?
Oh yeah, I think I did.
Okay.
Yeah. So I mean, I didn't bother proving it here. So I guess we've seen. Yeah, I guess we have seen it. Right. So and now just using that combined with this, I'm getting the randomized lower bound of log n. So good. The only thing left is this thing. I want to show you that a randomized approximate FP for p bigger than 2 requires n to the 1 minus 2 over p bits of space, which is optimal up to log factors. There's a result due to Indick and Woodruff from 05, I believe, that achieves that up to the log factors. And you can get a 1 plus epsilon approximation even. And people have been improving the dependence on 1 over epsilon and the dependence on log n in subsequent works. Right, and I guess I showed you the algorithm based on Andoni's note, the one using the exponential distribution. And p-set 2 problem 1 is about that algorithm as well, right? So you're familiar with this n to the 1 minus 2 over p. Where? This thing? This omega?
Yeah, you take a log of 2 to the over 0.
Right, so deterministic equality requires omega n communication. And the randomized private communication complexity of any problem is at least log of the deterministic one.
But you take log of 2 to the omega n.
Yeah, so 2 to the omega n is the size of C. By pigeonhole, the deterministic complexity. So maybe I'll. Right. So what I'm saying here is that the deterministic complexity of xc is omega n. Right. The deterministic complexity of xc is log the size of C by pigeonhole. But then the randomized complexity is always at least log of the deterministic complexity with the private coin model. So in fact, the randomized complexity of xc is at least log of the size of C.
So over here, when you say randomized approximate F0 should be omega of log n?
Yeah, that's right, omega log n.
You've written omega n.
Omega log n, yeah. So there is an omega n somewhere. So randomized exact is omega n, right? And that's what we showed by indexing. Randomized exact is omega n. Deterministic approximate is also omega n. But if you want both randomization and approximation, then the lower bound is log n, right? And in class, we had this algorithm for F0, maybe in the first or second week of lectures, where we showed that you can get kind of a, I think in class we showed a log squared n algorithm. But you really can get a log n space algorithm. Any other questions? Okay, so let me show you. Oh, yeah. Oh, sorry. S is the space of the algorithm alg. Okay. So let me show you this last lower bound, this FP lower bound. So first of all, let me define disjointness. And I should really say disjointness T. So is the following T player problem. Okay, and I should really say this is also going to be like the one-way. We're going to look at lower bounds from the one-way, although that's not really necessary. So there's Alice. Well, I can't say Alice now. Let me say there's player P1, there's player P2, there's player PT. So before we just had 2 players, we called them Alice and Bob. Now we have T players. In this problem, each player gets their own bit string. So there's x1 in 0, 1 to the n. There's x2 in 0, 1 to the n. And there's xt in 0, 1 to the n. Okay. And promised that either for all I not equal to j, xi intersect xj is the empty set. So when I'm using notation here. When I say intersect 2 binary vectors, I mean treat them as sets. Treat xi as a subset of 1 to n. Okay. So case 1 is that no 2 pairs intersect at all. Okay. And then case 2 is that for all I not equal to j, let's say xi, well, let's say there exists a k such that for all I not equal to j, xi intersect xj is exactly equal to k. Say again? Oh, so I mean, so in this case, no 2 sets intersect at all. In this case, every pair of sets intersects at exactly 1 point, and it's always the same point, k. So there is an element from 1 to n that's in every single set. And the disjointness T problem is to decide which. And how does communication work in this T-player problem? Basically, P1 is the one who starts talking. P1 can send a message to P2, who can then send a message to P3, et cetera, all the way up to PT. And if you were looking at let's say multi-pass streaming algorithms, or not just one-way communication, we would also allow it to go around. We would allow PT to then talk to P1, who can then keep talking, and we could keep going around like this. But for streaming, for one-pass streaming algorithms, we're just going to look at the one-way communication complexity where once it gets to PT, PT then just has to answer. Okay? And the way we're going to measure communication is the total amount of communication over the course of the entire protocol. So the sum of how much did P1 send to P2 plus how much did P2 send to P3, et cetera. We're going to look at that sum. OK, so before I tell you the lower bound for this problem, what's a trivial upper bound? N? OK, how would you do O of n? Right, so yeah, P1 could just simply send to P2. Right, if you're in one of these 2 cases, P1 can just send everything he has to P2 and then figure it out. We don't even need the other players to talk at all. Okay? What's something, now use randomization. What's something that beats O of n? I'll give you a hint. So in your comment just now, basically P1 and P2 could figure it out on their own, right? We don't need the other players. What's something they could do to take advantage of the fact that there are multiple players? So basically, P1 will talk to P2. And then if there actually is an intersection, they'll figure that out with a pretty good probability. If they don't figure it out, that's OK, because P2 will then talk to P3. And they'll catch it with good probability, right? So Basically, for if there's actually something in the intersection, for a randomized protocol to not find it, basically the communication between every pair of adjacent players has to fail, which is unlikely, right? So any ideas and how you could use this kind of idea to beat? So there exists a k such that for all I not equal to j, xi intersect xj is k. So if you look at any two players, okay, their intersection has exactly one element, and it's the number k. Right. So P1 can just send his entire set to P2, and they either intersect or they don't. Oh, but you're promised that one of these two cases holds. So you just have to check which of these two promises is the truth. Yeah, this is a promise problem. Well, okay, I'll just tell you basically. So the point is, roughly the point is, look at the support size of all these vectors. The average support size had better be less than n over t, right? If the average support size is bigger than n over t, that means the total number of elements across them is more than n, which means you definitely know that there's an intersection. So kind of the only interesting case is when the average support size is n over t, or less, right? Yeah. Say that one more time.
So if there's no intersection between the two pairs,
Yeah.
that means that any bit is allocated at most to one of the elements, right?
Well, not necessarily. So you're saying they can just figure it out by sending their support sizes over. But for example, maybe everyone gets a set of size exactly n over 2t, right? And the total number of elements is at most n over 2. Yeah, not every bit has to be present. So even though everyone has a set of size exactly n over 2t, there could still be an intersection in all of them, right? And you want to find out who that is. So kind of the interesting case to keep in mind is that everyone's set has size roughly n over t. If the average set size is bigger than n over t, then you definitely know there's an intersection. So everyone's set size is less than n over t. And then what P1 can do is just take a random subset of like a 1 over t fraction of his input subset and send it over to P2. Just like for each thing in his set, send it over with probability 1 over t. So you're sending only a 1 over t fraction of your set. And if there's something in the intersection, that intersected element will be sent over with probability 1 over t. Right? So P2 will catch it with probability 1 over t. And then P2 will do the same thing, send a 1 over t fraction of her subset to P3. And for no player to ever catch something in the intersection, the probability of failing is like 1 minus 1 over t to the t, which is like 1 over e, which is less than 1 over e. So it's less than a constant. So if you want a constant success probability, it's enough to do that. And each person, the average set size is less than n over t. Each person is sending in a 1 over t fraction. So each person is sending, like n over t squared bits. They need to send the indexes. That's an extra log n that I'm sort of not paying attention to right now. But that's a good point. They need to send the indexes as I'm saying it. But kind of really, everybody's sending n over t squared. There are t of them. That's like n over t. So the lower bound theorem, so the original prover, well, so there was a paper by Bar Yosef, Jairam, Kumar, and Shiva Kumar. I believe it was in 04 or 02. It's in JCSS 04. They lost the log somewhere, and they only got, they lost even more if it's not just one-way protocols. But there were improvements later, so there was Chakrabarty, Cote and Son, and then there was Gronemeyer, who was the first person to nail it exactly. This was in Stacks 09. And then JRAM gave an alternate proof to Gronemeyer's results. That was in Random, I believe in '09. And there's even older history if you look at just the two-player version of the problem. So I forgot who proved the, in two players, it was known that omega n communication is required, and that's trivial. Basically, Alice can just send her entire vector to Bob. And then there was another proof of that later given by Razborov, who's going to actually be here in a couple weeks to give a talk in our theory seminar about something else. And then these are these T-player versions, and they use this information theory, information complexity. Yeah. Yeah.
So one of those guys that are supposed to set over T, and only T sends supposed to the X.
Oh, I see. Oh, yeah. Actually, that's a good point. Yeah, that's perfect. So that's a deterministic protocol, right? So as you said, one of these guys has to have a set of size at most n over t by averaging. So he'll just send his entire set to the person after him. And that's, that would also have the extra log n in it. I don't see at the moment how to get rid of that, but yeah, it's a good point. So yeah, there's even a deterministic protocol, but this lower bound says that basically R pub, even there's a R pub of let's say final probability of third of disjointness T is omega n over T. Okay. In fact, there's even it's even true, I think, in the distributional sense. There's a hard distribution that such that any deterministic protocol for that hard distribution requires n over t. Okay. So, by the way, notice the total communication is n over t, which implies that some player sends omega n over t squared bits. Right. So since the total communication is n over t, there is a player that sends n over t squared. And now claim for p greater than 2, a 1.1 approximation to fp, let's say randomized, a randomized 1.1 approximation to fp requires omega n to the 1 minus 2 over p bits of space. And that was one of the motivations for the Bar-Yosef et al. Paper, why they were looking at this problem, to get a good lower bound for this. And the proof of that, set n, or t, to the n to the, let's say 2n to the 1 over p. Okay. I should mention in the proof of hardness for disjointness, it's also the case that kind of every set in the hard example has size, n over 4t or something like that. Okay. Or some, you know what the set sizes are. They're all exactly n over t times some constant. So what's the reduction now? There's a reduction from disjointness t, as you might imagine. And it's the usual thing, right? The usual thing is, actually, I don't even need to use the fact that all the sets are the same size. The usual thing is P1 will treat every one in X1 as an element of the stream and put it in. And like when he finishes processing his set, he'll send the space of the streaming algorithm, the memory contents, to P2, who then runs it on X2, sends the memory to P3, and everybody just keeps running the streaming algorithm. Okay. Now, let's say there's case 1. In case 1, no one intersects. So everyone in the stream has frequency 1 or 0, at most 1. So this means that FP is at most n, right? 1 to the p is 1. In case 2, there is some index k that's in everybody's stream, right? So the weight of the frequency of k is going to be t, which implies that fp is at least t to the p. Right, by definition of t. So if you have better than a 2 approximation, you can distinguish these cases QED. Right? Some player sends, since the disjointness lower bound is n over t, some player sends n over t squared bits. But how many bits is each player sending? Each player is sending exactly s bits. Right? They're sending the space of the streaming algorithm. So this implies that s is at least n over t squared, which is omega n to the 1 minus 2 over 3. So once you have the disjointness lower bound, it's straightforward to use it. The hard part really is proving the disjointness lower bound. Okay. By the way, just I mean, there's a more straightforward way to say this, but just so a trick to keep in mind. What if I wanted to prove, so what about L infinity norms? So here's LP norms, L infinity, so P is infinity, right? What's one way to get that out of this? One way to get it out of this is basically look at two-player disjointness. Two-player disjointness requires linear amount of communication, and if Alice and Bob's two sets intersect, then the L infinity is 2. If they don't intersect, then the L infinity is 1. So if you have a 1.1 approximation, you can tell the difference. Okay? Notice that L infinity, that's basically what this says as well, because L infinity is basically the same thing as the infinity norm is basically the same thing as the log n norm. That follows by Holder's inequality. So that's something to keep in mind, right? Infinity norm and log n norm, where the dimension is n, are basically the same thing by Holder's inequality. So I'll let you think about that offline. But then n to the 1 over log n is 2. And 2 times 2 is 4. So again, what this proof is saying is for L infinity norms, you should do disjointness with a constant number of players, which you can do it with 2 players. Anyway. Any other questions? So that's all I want to say about lower bounds, and I want to start doing some non-streaming stuff now. So if you have some streaming questions, speak up. Even though I'm saying that we're done with streaming, as you're going to see, everything's the same. I mean, we're gonna go to another topic, and the techniques that we're going to start using over there are going to start looking a lot like things that we analyzed when we were doing streaming. So, these different topics that we're going to see in this class are all quite connected. And so, chapter 2 is dimensionality reduction. Just to make sure everybody realizes that we're done with streaming, maybe we should have like not a moment of silence, but something to commemorate this. So maybe let's have a moment of silence. Okay, so okay, good. That's enough. That's enough of a moment. Okay, so now let's move on to another topic, which is dimensionality reduction. And okay, so the point of dimensionality reduction is we're given an algorithmic problem with high dimensional vectors as the input. So you're given an array or list of high dimensional vectors, and you have to solve some problem. Okay. Nearest neighbor search. Or maybe large-scale linear algebra problems, large-scale regression problems. Or some other. I mean, there are lots of, I could keep going, minimum and closing ball, etc. So think computational geometry, but high dimensional. So for example, nearest neighbor search, people do this kind of thing. They take input like images or documents, web pages, and they vectorize them, right? So an image is naturally, let's say you have 1,000 pixels by 1,000 pixels. That's just a million-dimensional vector, which every inch in the vector tells you the intensity of that pixel. Or maybe you featureize it in some other way. But the point is you turn your input into high-dimensional vectors, and then you want to solve problems like find me, given a query image, find me an image in your database that's as close to the query image. Okay, so that's a nearest neighbor problem. We'll see. There's clustering problems where you're given lots of data and you want to cluster the data based on some kind of similarity metric. So we'll see various problems, but the goal of dimensionality reduction is quite simple, or the motivation. So as you might imagine, if you're given an instance of one of these problems, kind of the higher the dimension is, the harder it is to solve the problem. Okay, like we're going to develop, there are algorithms that solve these problems. The runtimes depend on the dimension as well as the number of points. And the more the dimension goes up, the more the runtime goes up. The more the space consumption of the algorithm goes up. Okay? Or if you want to communicate, if I have some data and you have some data and we're in a distributed setting, for me to send you parts of my data, the communication goes up if my data is higher dimensional because I have to send a longer vector to you. Okay, so the goal here, there are a few goals, fast runtime, let's say low storage, low communication. And to get these things, one thing to do is to have low dimensional input. And dimensionality reduction is basically a pre-processing step where you're given, before you even run whatever algorithm you're going to run, you're given this high dimensional data. You run it through a pre-processing step, which we'll talk about for the next few lectures, that makes the data lower dimensional, okay, while preserving some structure. And then now you run whatever algorithm you're going to run on this lower dimensional data. And it's faster, and it uses less memory, et cetera, et cetera. Okay, so geometric structure, what does that mean? Distances between different points. So you have to fix your metric, but you want to map down to lower dimensional while preserving distances, or maybe you want want to preserve angles, or maybe you want to preserve, take any, so what's the distance? Take any two pairs of points and look at the length of the line between them. And maybe you want to do a higher dimensional version of that. Take any subset of k points. You want to preserve the volume of their convex hull. So volumes of subsets of points. Or more generically, something you might want to preserve is just there's some problem you want to solve, like clustering. K means clustering or something. You want to preserve optimal solution to some geometric optimization problem. Okay, and sometimes to do this, it's enough to preserve distances. Sometimes there's something else you want to preserve. Sometimes you can do better if you just want to preserve this as opposed to all distances or something like that. Okay. And today, in the remainder of today, we want to preserve distances. Okay, so let me give you a definition. So what do I mean by preserving distances? I'm going to talk about distortion. And it's like a worst case form of preserving distances. I give you a set of vectors. They're high dimensional. I want you to map them to low dimension such that all the distances in this set are almost the same as the distances in the original set. So given two metric spaces x dx and y, don't worry, there's not much, so analysis is not a prereq for this class, but I'll just say what's a metric space? It's a point set together with a distance function. Distance function should satisfy what you think about distance functions. Triangle inequality. They're symmetric. The distance between x and y is the same as y and x. The distance from a point to itself is 0. Okay, and if the distance between a point and another point is never 0. Okay, so that's what a metric space is. So given two metric spaces and a function mapping, let's say, one metric space to the other, one set of points to the other set of points, we say f has distortion at most df if for all xx prime and capital X, we have the following inequality. Okay, we have, if you look at the distance in x between, so if you look at the distance in y between f of x and f of x prime, it's at most c2 times the distance in x between x and x prime, and it's at least c1 distance in x and x prime, where c2 over c1 is at most the distortion. Okay, so maybe think about c1 as 1. What I'm saying by having distortion df is look at where x got, for any pair of points x and x prime in the original metric space, look at where f mapped it in y. So f of x is an element of y. So I'm mapping x to y. So f of x is in y, f of x prime is some other point in y. The distances should be at least as what they were before, and they shouldn't blow up by too much. They shouldn't blow up by more than df. Okay? So we say that a map has distortion df if that's true. All the distances are kept roughly the same up to a factor of df. So today we're gonna, or really the rest of this class, when we talk about dimensionality reduction, we're gonna focus mostly on like normed metric spaces. So the distance between two pair of, right, normed vector spaces. So the distance between two vectors x and y is the norm of x minus y for some norm, LP norm or whatever other norm. Okay, good. Okay, we will focus on normed vector spaces. And what I mean by that is the distance between x and x prime is just, for some norm, it's the norm of x minus x prime. Okay. And we want to have like really good dimensionality reduction. So we're going to, I'll show you, well, let me just claim it now. So there's a theorem. This is due to Johnson-Lindenstrauss. In '84. It's often called the JL lemma. Okay. Which says that for any set of points, x1, x capital N, in L2n. So these are little n dimensional vectors, and we measure distance in L2 norm. Okay, so let's say that x is x1 up to xn. There exists a matrix and also I should say for all epsilon. For all epsilon, for all sets of points, there exists a matrix with the number of dimensions being 1 over epsilon squared times log n, the number of points. Notice it doesn't depend on the original dimension at all, just the number of points, such that the map x goes to such that pi mapping capital X to L2M has distortion at most 1 plus epsilon. Right, what does that mean? There's a linear map, so xi gets mapped to pi xi. You're multiplying by this matrix pi, right? So the pi is an m by n matrix, so your original vector has little n dimension. It now has little m dimension. Little m is 1 over epsilon squared log the number of points. So for any set of capital N points, you can map them to log capital N dimensions such that all the distances are preserved up to a constant factor. In fact, up to 1 plus epsilon if you make it 1 over epsilon squared times log capital N dimensions. Okay, so this is one form of dimensionality reduction. It's for preserving L2 distances, Euclidean distances, while mapping to very low dimension. And we're going to mostly focus on L2. So we'll spend quite a lot of time focusing on L2, and you might ask why. Why don't we look at L1 or L infinity or some other LP? So first, let me say, after JL had this thing in the 80s, people started asking those kinds of questions. Why don't we do this for L1, et cetera? Brinkman and Charikar, I'm now forgetting the year, they showed the following. basically for L1, dimensionality reduction with distortion C, there exists a set of endpoints. So for any n, there exists a set of endpoints requiring dimension m, which is at least n to the omega 1 over c squared. So whereas we were getting like log dimension over there, they show that if you want to do it for L1, you really need polynomial dimension. Okay, so you can't do as good a job at dimensionality reduction in L1. And actually, there's a paper by Andoni, Charikar, Neyman, and Nguyen. This is, I guess, Fox 11. That says, see, if you want distortion, not just a constant, but you want 1 plus epsilon distortion, just like what you're getting in JL, that implies that m has to be at least, there is a set of points such that you can't map to low dimension unless m is at least something like n to the 1 minus o of 1 over log 1 over epsilon. So if epsilon's tiny, this is like almost linear. So you can't really like do anything, is basically what they're saying. And there's another theorem which is even kind of more a hint. So this is all L1. I mean, maybe what about L1.5? Maybe you can do something there. So there are theorems that say that give lower bounds that basically hinted that L2 was really a special case and it's the only thing where you can do good dimensionality reduction. And that was made more formal by Johnson and Naor. Okay, so let me make sure I say this. So by the way, these lower bounds are not just for linear embeddings, right? This says no matter how you do your embedding, no matter what f you use, right? No matter what f you use, where's f? There, that f. You can't beat these target dimensions. Okay. So Johnson and Naor said, they basically said that if you want to use a linear embedding and map to log n dimensions, or at most log n dimensions, then you can really only do it if your original space is like almost the same as L2. So they say the following. Suppose, I don't want to get too mathy, so I'll suppose, let me use the chalk. Suppose x d is or let me call it, it has a norm. It is a complete normed vector space. Okay, this has a name. It's called a Banach space. Okay, so don't worry about the formality. If you have some normed vector space such that for any endpoint subset of x can map to an ON log n dimensional subspace of x with constant distortion, right? So that's what the JL lemma says, right? It says that for any endpoint subset of L2n, you can map it to a log n dimensional subspace with constant distortion. So suppose you had a vector space such that for any n-point subset you can map to log n dimensional subspace of X with constant distortion. Then what their theorem says is that then this norm space X is almost the same thing as L2. Then every n-point, or not n-point, n-dimensional linear subspace of X embeds into L2 with distortion at most 2 to the 2 to the O of log star n. Okay, so do people know what log star n is? Log star is the number of times you have to take log to get down to 1. So if you look at 2 to the 2 to the 2 to the 2, that's a really big number, right? 2 to the 2 to the 2 to the 2, so that's like 2 to the 2 to the 4, which is like 2 to the 16. And 2 to the 16 is, I guess, around 65,000 and change. Just add another 2, then you have 2 to the 65,000. Okay, so that's a ginormous number. But log star of that number is just 5, I guess, because, or 5 or 6. How many times you have to take log of this tower of 2s to get down to 1? Every time you take a log, you reduce the height of the tower by 1, right? So log star n, for all practical purposes, is like 5 or 6. Okay? So what their theorem is saying is that if you have this JL kind of property where every finite point subset maps to log dimensions, then the space, every linear subspace of your vector space, of your norm vector space, basically is almost the same as L2. It embeds into L2 with like tiny distortion. So this really says like L2 or things like L2 are very special. Okay. And in fact, they have a lower bound. You could say, well, maybe I could get a constant here. They show that there is a Banach space, Y, such that for any n, there is an n-dimensional linear subspace of Y that does not embed into L2 with distortion better than 2 to the alpha n, where alpha is inverse Ackermann. Okay, so anyway, random fact. So the point of this and, oh, why did I leave that there? The point of that and this is just that L2 is special. Okay, so we're going to focus our attention on L2. So we're going to prove this JL lemma. And before we prove the JL lemma, we're going to prove it using something called the distributional JL lemma. It says that for all dimensions n, and for all let's say epsilon delta in between 0 and 1/2, that's a 2, there exists a distribution d epsilon delta, which is a distribution on matrices, which are m by n, with m being at most up to a constant 1 over epsilon squared times log 1 over delta. Such that for all x, the probability over pi being drawn from this distribution, the probability that pi does not preserve the norm of x Notice that since pi is a linear map, if you preserve all the unit norm vectors, it implies that you preserve all the vectors, right? So we could even say that for all x in Rn, such that the norm of x is 1, and then this thing here is just 1. So let me rewrite that. The probability that pi x L2 norm squared minus 1 is bigger than epsilon is at most delta. Okay, so this is the distributional JL lemma. By the way, just given your streaming experience now, we want a random matrix that preserves L2 norms of vectors. Does that sound familiar? That's like the AMS sketch, right? Or the thing you did in your P set. So in fact, what's pi going to be? It's going to be a random sign matrix. Okay. That's how we're going to prove this. So you've already seen this. Okay. You've basically already seen it. I mean, the AMS sketch, we analyzed using we analyzed in the case that delta was a constant. You want to succeed with probability 2/3. And we showed that m could be 1 over epsilon squared. Okay? And we did it using like an expectation variance argument and use Chebyshev's inequality. If you want to use Chebyshev's inequality and get failure probability delta, it's going to force you to set m to be something like 1 over epsilon squared times 1 over delta. This is going back to even like lecture 1, lecture 2, when we're doing Morse plus, etc. Right? And the way that you can get log 1 over delta is, back in the streaming world, get failure probability 1/3, do lots of these in parallel, and take the median. Okay. Once you take the median, though, it's no longer an embedding into L2, right? Because what is an embedding into L2? It's a function mapping vectors in L2 to vectors in L2, meaning the embedded vector, like the image, the way that you measure its L2 norm should be you take its L2 norm. There are no medians here. So really what we want is that even after you apply pi to this dimension, the L2 norm is still what it should be with high probability, probability 1 minus delta. Right? And we don't want to have a dependence on 1 over delta. We want to have a dependence on log 1 over delta. And the way that we're going to do that is by using, well, the variance argument was like, the Chebyshev argument was like a bound on the second moment. Does that sound familiar? You bound the second moment of your estimator random variable, and then you use Chebyshev. The way that we're going to get this kind of bound is by using the same exact pi, the random sign matrix, but instead of bounding the second moment, we're going to bound the log 1 over delta moment. And we're going to see that that's going to let us get away with a smaller m. M just needs to be log 1 over delta. Anyway, questions about that? So before we prove distributional JL claim, I claim that DJL, distributional JL, implies JL. If we proved this theorem, it would imply the JL lemma. Proof: set delta to be less than 1 over n choose 2. Okay. And look at the set of vectors. Look at the set of vectors T, which is xi minus xj over the norm of xi minus xj. Okay. Say I less than j. Notice that the size of T is exactly n choose 2. Okay. Now, for some matrix pi, what does it mean that pi doesn't have distortion 1 plus epsilon? For pi not to have distortion 1 plus epsilon, it means that pi failed to preserve the norm of one of the vectors in T. Okay? So the probability over pi that pi doesn't have distortion 1 plus epsilon on that set of vectors x is the same thing as the probability over pi that there exists a z and t such that pi z L2 norm squared minus 1 is bigger than epsilon. That there is something in z that it didn't preserve. But by a union bound, this is at most the size of t times the probability for a single one of them, which is delta. Right? And that's strictly less than 1, because delta is less than 1 over n choose 2. So the probability that pi doesn't have distortion 1 plus epsilon on x is strictly less than 1, which means that with positive probability, it actually preserved everything. And then the final dimension you need is 1 over epsilon squared log 1 over delta, which is the same as 1 over epsilon squared log capital N. Okay? Questions? Okay. So we have just maybe 3-4 minutes, so I won't write anything. I'll just tell you where we're going next. So next lecture, what we're going to do is we're going to prove the distributional JL lemma. Okay. The way we're going to do that is we're going to prove some tail-bound inequalities and introduce methods for proving tail-bound inequalities. So we've already seen some, right? We've seen Bernstein inequality. We've seen Chernoff bound, Chebyshev's inequality. Now, kind of the difference, one kind of fundamental difference between this kind of tail-bound versus the ones we've seen before, or like this tail-bound, the ones we've seen before, is this is, let's say pi ij. Let's write it as sigma ij over root m. So it's like it's a scaled random sign matrix. Sigma j is a random sign. Before we were used to proving tail bounds on sums of independent random variables, like the Chernoff bound. A sum of independent random variables is like kind of a linear form in those independent random variables. Here, this is like something L2 norm squared. It ends up being a quadratic form. This is like a degree 2 polynomial in independent random variables. So we need to develop a way to handle higher degree forms for tail bounds. So we're going to see that next lecture. There's something called the Hansen-Wright inequality. And then once we prove the Hansen-Wright inequality, distributional JL is like a corollary, essentially. And then we're going to use the Hansen-Wright inequality to prove other things too, like other forms of JL that are more efficient, et cetera. So I think I'll leave it here for today. Any questions? Okay. And the P set was extended. It's due tomorrow before midnight. Okay. Okay.